welcome to YouTube channel Electronics for You. In this video, I will explain balanced and unbalanced star connection, in which I will first explain balanced load and unbalanced load. Later on, we will cover main topics of star connection, that is relationship between voltage and current, then power in star connection, and lastly we will see the vector diagram of star connection. So friends, before this video, I have made one video where I had explained star and delta connection in detail. So if you haven't seen this video and you don't know anything about star delta connection, please watch the video, the link in description. So here are some terms related with star delta connection. The first one is VPH, that is phase voltage. It is the voltage across a phase and it is known as phase voltage, denoted by VPH. Then the term is phase current. It is the current which flows in phase is called phase current, and that phase current is denoted by IPH. Next term is voltage between any two lines is called line voltage. That is, if we measure the voltage between any two phases, then it is known as line voltage and it is denoted by VL. The last term related with this is the current which flows in the line is called line current. So the current which flows in our transmission line, that is the output lines of the star or delta connection, it is called as line current and it is denoted by IL. Now let us see what the balanced load is. If all the phases of three-phase load has same impedance, then such a load is called as balanced load, that is Z1 equal to Z2 equal to Z3, because in star connection or in delta connection we are having three impedances, and if these impedances are identical, then such a load is called as balanced load. This is a balanced star connection where each impedance is 10 ohm. Similarly, we can have a balanced load of 8 ohm in our delta connection also. So this is a balanced delta connection because all the resistances are here, all the impedances are here of 8 ohm. The next definition of balanced load can be when current in all the three phases of the load is equal, then it is known as balanced load. The second definition will be this one. This is related with the current, and if the current is having same value, then it is also called as balanced load. For example, the example of balanced load is induction motor, three-phase induction motor especially. Now let us see the characteristics of three-phase balanced load. A balanced load is always having all the impedances of same value. Then current in each phase is again same. Look here that impedances are same, current is also same, but having phase difference of 120 degree from each other. Similar case will be in case of voltage. Here the voltage across each phase is again same and having a phase difference of 120 degree with each other. In case of three-phase balanced load, the active and reactive power is same in all three phases. That is, its current, voltage, power and impedances are same in case of a three-phase balanced load. Now let us see the star connected balance system here. This is a star connected system. You can see, let us assume that these impedances, the impedances of these three coils are same here, and it is connected across another load that is having ZR equal to ZY equals to ZB, that is all the three impedances are same here. Then such a system is called as balanced system. In this case, ZR equal to ZY equals to ZB and having same phase angle between them. And in this case, therefore we can say that the magnitude and phase angle of three phases of load must be equal. Now let us move to the next important topic. It is star connected balance system. Now in this case we are having a winding, or we can say that a phase, therefore it will have some inductance and some resistance, and total impedance will be Z1 Z2 or Z3 in this case. So we are having three impedances for which are nothing but same, because here each impedance is having 1 Henry inductance and 2 ohm resistance. So we can say that Z1 equal to Z2 equals to Z3 in this case, and this is a star connected balance system. It is balance system because all the impedances are having the same value, and in this case we are having this point. This point is common for all the impedances, and this point is called as neutral point, generally denoted by N here. So both figure are showing the similar things. Here if we consider IR as IR, IY and IB as the phase current for red, yellow and blue wires respectively. Similarly, we may have the voltage across them as VRN, VBN and VYN, etc. These are called as phase voltage. Similarly, if we measure the voltage across any two phase wire, then this is called as the line voltage, and in this case let this voltage, that is if we measure the voltage between red wire and yellow wire, it is called as VRY, and it is nothing but our line voltage. So in case of three phase balance system, this voltages will lag from each other by 120 degree. If we consider as our main sequence as VR, VY and VB for our red, yellow and blue phase respectively. So in this case the neutral wire is having phasor difference as IN equals to IR plus IY plus IB. Note here that this is the phasor difference and the direction of current will have important here. Now let us find the current and voltages in our star connection. Now see, this is our diagram. Here in case of phase voltage, the definition of the definition of phase current is the current flowing through phase, and the definition of line current is the current flowing through line. Now in this case the current flowing through phase is IR. Similarly the same current will flow through the line IR here. Similarly here it is IB and here this is IY. So we can say that the current will always flow and it is same, that is phase current equal to line current, or we can say that IL equals to IPH in this case. Now let us talk about the line voltages. Now we are having this as our line voltage. Let us denote this by VRY because it is in between red and yellow. So let's denote it by VRY. We can denote this voltage as VYB and the line voltage across these 2 points we can show it by VBR. We can say that it is VBR. So these are the three line voltages which can be measured between any two phases, and in this case you can clearly observe that here VRN and VYN are actually different, and they are, if we apply KVL here, it will have some value, and it can be seen here by Kirchhoff's voltage law that VRY equals to VRN minus VYN, because these are having two different directions. So if we move like this, then VRN can be taken as positive and VYN will be taken as negative, that is it is subtracted from this, and therefore VRY equals to VRN minus VYN. Similarly if we measure this, again these are having two different directions, and therefore VYB equals to VYN minus VBN. Similarly VBR equals to VBN minus VRN. Note here that all the voltages are here in vector form. Now let us calculate the relationship between this VRY, VRN and VYN, but for that we will require the vector diagram or phasor diagram, because if you want to find out the relationship between different voltages here, so let us find it by using the vector diagram or our phasor diagram. So in this case we are considering our reference voltage as VR, because it is our first sequence of the voltage, phase voltage. Therefore let us take it as VR. Now we know that each resistances is each voltages, that is phase voltage, is having its negative direction also, that is minus sign is there. Therefore this, if this is VR, and we can show V minus VRN in the exact opposite direction. Now this is our red phase voltage of red wire. Now blue phase is actually RY, yellow phase is actually 120 degree apart from this, and therefore it can be shown just like this. Here the phase difference between this red and yellow is 120 and it is VYN. So VYN is having positive direction in this way, and exactly in opposite direction we will get its negative, that is minus VYN, can be shown like this. Now third phase, that is blue phase, is having again phase difference of 120 degree from VYN, and therefore it can be shown like this, and its negative counterpart will be minus VBN, and it can be shown like this. Okay, now we are having this as our neutral point in this case. Now neutral, instead of calling it as neutral point, let us say it is 0. Now in this case, if we want to find the line voltages, that is the voltage between a red and an yellow, then we have to draw the parallel lines to this, and this can be drawn like this. Similarly to this red, we are having parallel here. Now its resultant can be shown starting from this point and terminating to their intersection, and it is nothing but in between VR and VY, therefore it is VRY. So this is our first line voltage VRY. Note here that VRN, VBN, VYN, all these are our phase quantities. Now again calculate. Now let us have a parallel line over here for this yellow and for this blue, and if we connect it, again we are having this. Now the resultant can be VYB, just like this. Now next one is this one, and here the resultant is VBR. So in this way we can plot a vector diagram. Here note that we are having a phase difference of 120 degree, and it is minus 120 degree, which can be shown by in clockwise direction. So we have just plotted this and we got vector diagram in the star connection. All voltages are shown here. The current can also be shown, which is having some phase difference here. So we can show IR here, IY here, and IB here, which will lag the voltages by some angle. Not exactly 90 degree, but definitely it will have some angle which is less than 90 degree and greater than 0. So this is the vector diagram for a star connection. Now using same diagram we can further plot. This is our diagram. Here we can calculate the relationship between a phase voltage and a line voltage. Now let us assume in this case we are having a triangle as L, M and N respectively. So this is L, M and N points that we are having, and we have already said that VRY is equal to VRN minus VYN. Now in this case, if we apply cos angle here, so let us assume that this is angle phi here, and it is cos 30, because this angle seems to be 30 degree. Total this phase difference is actually 60 degree, so this will be half of that, and it is 30 degree. In this case cos 30 is equal to adjacent side divided, adjacent side divided by hypotenuse, and therefore it is NL divided by MN. Here this one is nothing but bisecting this perpendicular. Actually this perpendicular is bisecting this line, that is VRY, and therefore we can say that it is half of VRY, NL equal to half of VRY. Similarly MN equals to VRN. This is an M line and it is the phase voltage VRN. Now we are having this value as well as this value, and cos 30 is equal to under root 3 by 2. Therefore putting value here, under root 3 by 2 equal to half of VRY. VRY is nothing but line voltage, so I replaced here VL, and VRN is the phase voltage, therefore it is replaced by VPH. Now note that this and this part will get cancelled, and we will get VL equals to under root 3 VPH. So this is the formula for line voltage. Line voltage is equals to root 3 times VPH, that is phase voltage. So this is the relationship in case of a line voltage and a phase voltage in case of a star connection. Same way, this is one way where we can calculate this by using geometry, or we can have another option also, where we can calculate again the same, that is VRY. Let us assume that this is A and this is B. Now here this VRY can be given by under root A square plus B square plus twice AB cos phi or cos theta, let us say. Now in this case further the phase angle will be here, this one, that is VRN and VYN are VPH here, and therefore we are putting here phase voltages, then twice phase voltage. Cos 60 degrees here, because now this angle is the angle between VRN and VYN. Minus VYN is actually 60 degree, therefore putting cos 60 here, which is equals to half. Now this 2 and this 2 will get cancelled, and we will get VL equals to under root 3 times VPH square. So further solving it, we get VL equals to root 3 times VPH. So this is another way where we can calculate again same relationship, that is VL equals to under root 3 VPH in case of a star connection. And we have calculated it for a balanced star connection. Now let us talk about the power in case of a star connection. Again, balanced star connection, the first formula will be for active power. Now we know that power can be given by VI cos phi. So here the active power is P is equals to, in case of if we write it in terms of phase quantities, then it is 3 times VPH IPH cos pi. 3 here indicates that our 3 phases are there. Now same formula can be written in terms of line quantities, as because we have already calculated it, it will be equals to under root 3 times VL IL cos phi, because VL equal to root 3 times VPH here, and if we put the same value, we will get here P is equals to under root 3 VL IL cos phi, because IL is equals to IPH in this case. This was the actually real power, that is active power. Now let us find the reactive part of power, that is imaginary power, and its formula, it is actually indicated by Q. Here the unit for active power is watt, whereas in case of reactive power its unit is VAR. Here in case of in this case reactive power can be given by 3 times VPH IPH sin pi. Note that cos phi is just replaced by sin pi here, and this is our reactive power. Similarly, we can calculate apparent power by using formula S equals to under root P square plus Q square. Now put any two quantities here for the phase or for the line, and we will get S equal to under root 3 VLIL, or we will get it is equals to 3 times VPH IPH. So this is our apparent power in case of a star connection, balanced star connection. Now let's talk about the unbalanced load. In previous section we have seen the balanced load, where each impedance was having same value. Now in this case, if all the impedances are having different values, then it is known as unbalanced load. Now this is the example of unbalanced load, where you can see that Z1, Z2 and Z3 are not equal to each other. And for delta connection also, you can see here that all the resistance, all the impedances are having different values. Now same again we can define in terms of current, that if all the currents are different, then it is called as unbalanced load. The example is in example for the unbalanced load is factory load, or the load having power distribution in a locality. Now let us see the characteristics of a three-phase unbalanced load. So it was unbalanced load, therefore impedances will be different. Similarly, current flowing will be different. Similarly, voltages will be also different, and there is a phase difference of there will not be a phase difference of 120 degree. That is, the phase difference will be other than 120 degree. Now the power can be calculated by addition of all the phases here. So it is P is equals to VR IR cos phi, VI IY cos phi. Similarly, VB cos IB cos phi B. Note here that again phase or angle will also be different, and therefore here phi R, phi Y and phi B is written. Same, if we replace cos by sine, then we will get reactive power, and apparent power is VRIR plus Vy Iy and Vb Ib respectively. So this is a three-phase unbalanced load. In case of star connection as well as in case of delta connection, it will remain always same. Now let us see one of the vector diagram in case of unbalanced star connection. So in case of unbalanced star connection, generally the VR, Vb and Vy will have different magnitudes. Similarly, they are having phase angle between them as different, and therefore we will get waveform like this. Note that this is one of the diagram. It can be anything depending on the values of VR, Vy and Vb. In this case, VR is not equals to Vy, is not equal to Vb. That is the unbalanced star connection. So in this way we have seen balance and unbalanced star connection. In next video, I will explain balanced and unbalanced delta connection. So keep watching. Thank you.